University of Tokyo, and present also professor in University of Tokai. Yeah, and been many friends, many professor, leader in Japan's sensei. So, Sensei Uyeda, please. I hope you.
Thank you very much, Jordan, Professor.
Yeah.
I first would like to thank Taiwan government and people for helping us after Tohoku earthquake. Taiwan is one of the most efficient countries to help us. And today my talk will be very simple in the way of science, but it is just like that. Earthquake prediction in Japan and 311 magnitude 9 supergiant earthquake, it's the Tohoku earthquake. So essentially the talk is two parts, and I suppose I will run out of time about here. In that case, I'll stop there. Okay. And what I'm going to talk about is Japan is good at earthquake prediction. No, just contrary. Okay. And just for the people who are not really associated with this business, let me start from the very elementary. Earthquake prediction, you need when, where, how strong. And as to when they're long, intermediate, short term. In my idea, long term has no use. Mid term has no use. Early warning, it is not even prediction. Okay, well, really important is a short term prediction. Useful. For that purpose, precursors are needed, and high accuracy is needed, and immediately checked, can be checked. Therefore, come on, this is the prediction, earthquake. So when I talk about earthquake prediction, it's only about short-term one. I don't care about these things. Okay? I will show you how next day. So, most important is a short-term prediction, and for short-term, precursors are absolutely needed. Okay? The most precursors are non-seismic, because seismometers record only earthquakes. What we are interested in before the earthquake. Okay? So, okay, those precursors are mainly electromagnetic anomaly, cluster deformation, underground water anomaly, and so forth. And sometimes seismicity can play some role, but not the case, no. Macroscopic anomaly, animal behavior, and so forth, right? But these cannot be measured by seismology anyway. Okay, right. So I'll just show you how stupid what long-term prediction was. This was a prediction made some time ago by the Japanese government, and this shows only the probability distribution for the next 30 years for certain intensity of earthquakes in Japanese scale. And these are the epicenters that took place after that. And look at this. They are not where the probability is any high. Sometimes, yes, but most of the time, no. Okay, so, okay. So, my first statement is, in Japan, there is no real earthquake prediction research. There is no. Why? The answer is simple. National program started in 1965, almost simultaneously with USSR, China, USA. And seismologists dictated the program only to improve their seismic networks. They spend all the energy, money, staff to seismic networks. No short-term prediction is possible, therefore. Therefore, there was no prediction. In all this, some half a century program during this time, there was no prediction. Of course, there was no success, and there was no failure either. So they say, we have no failure, but they didn't have any prediction made. So the whole thing is rather silly. Why? At the time of Kobe earthquake, this is Kobe, okay? Right. There was a strong criticism against this long, useless program. And that they claimed that precursor was too difficult to find, and no one can find it. They decided that. This is a decision. So they said, let us stop short-term prediction research. Stop. Therefore, this is why there is no real research on earthquake prediction now in Japan. If you have any question, you can interrupt me. Right? Okay. So how did this happen? They knew the precursors are needed, and seismic observation is not good. Still, their vested interest, shared by, a group of seismologists and bureaucrats were too strong to change the policy. They have established a group, what we call village of earthquake prediction. But earthquake prediction is always top of priority of research nationally all the time. So they cannot stop giving money. So they give money and say, we give you money even if you stop research. That is what is going on now. Thus they succeeded in establishing a system for permanent budget for basic study without prediction. So no more research. But the thing is that general public does not know about it. So general public still believe earthquake prediction research is actively going on by many seismologists who cannot do it. But this is the great difference between public notion and reality. Okay? All right. I can go back if you like. I don't spend any more time, but just to show you. Oh, can we go back?
Go back.
Go ahead.
Go ahead.
The total budget is about 120, 100 million per year, and this is a circle. And only a very small fraction goes to the university. It's about 400 million. And with this 400 small amount, this only portion goes to the short-term prediction research. So it's practically zero, nearly. Okay. But since all the money goes to seismology, Japan is full of seismic stations, high-powered, long-term, broadband, everything like this. Okay. So this is the situation. However, there are signs that earthquake prediction is possible by non-seismic precursor research. This is a group I belong to. In particular, radon emission and electromagnetic precursory phenomena, because science in these aspects is rapidly advancing in many cases and many countries. Actual successful predictions have been made, really. This is an interesting statement. Most seismology people become my enemy. The precursors do not cause the earthquakes. They do not cause the earthquake. Of course not. So, that no elaborate theory of seismology is needed for prediction. You don't need it. So, maybe seismology is not even needed. Okay. So here's an example radon. And this is the Kobe area. This is the Kobe earthquake epicenter. And the fault goes like this. And this is where they are making measurements. And this is a 10-year record of radon in air. And it went up, shooted up like that, and there was an earthquake, the earthquake. So evidence really looks looks rather strong, but they completely disregard all these things. They pay no attention. Time is very short, huh?
It's okay, because next two speakers, your student.
I should stop that. An example of successful prediction. It's a Van method. It's invented in Greece. And they are making continuous monitoring geoelectric potential variation called SES. And this has been successful over 30 years already. And it's getting better and better. Go ahead, please. Now these are Augustus and his wife, and we are all very young, some 20, 30 years ago. Okay. Okay. And this is just an example showing this during this period. I put all the earthquake greater than 5.5 in magnitude. Okay, right. All this colored one is successfully predicted, and red one was not quite good.
Timing. You start. It's okay.
Okay. Yeah. Right. Right. Next.
Next.
And this is Dr. Velasquez nowadays. He's getting old, as I am getting old too. Okay. The reason for the success of Van is very simple in physics, but very hard to achieve. You have to be really devoted to this Van. Success in noise rejection, that is an important thing, by multiple observation dipoles. This is very simple in physics. This is one of their stations. These are all measuring dipoles. And this is 1 kilometer. The size of the area is rather large. And a station like this is very difficult to set in Japan, because Japan has a lot of electric trains going around. And in Greece, there is no electric train in this area. So they can be free from noise and can be very successful. Okay. Not very easy in Japan. So in fact, there are two types of short-term electromagnetic signatures, precursors. Emission from the focal zone, that's like Van method. And the other one is rather interesting, which we call light coupling. Lithosphere, atmosphere coupling. That means ionosphere is disturbed before the earthquake by something going on deep in the earth. It's hard to believe, but the evidence is very, very strong nowadays. Very strong in Russia, Mexico, Japan, everywhere. Okay? And let me just go back a little bit about Van station situation in Japan. We started Van type of work 1996, just after Kobe, and we put all these stations. But in a few years' time, Japanese government decided earthquake prediction is not possible. So we had to stop everything. Anyway, so here's the one station, Iwate-san, and big earthquake the other day was just taking place here. So if we had a station working there, we could have got some useful data, but there's no station anymore. Okay, right. Just one example, this is a Iwate station, and our stations are just like simple like this, not many dipoles like the Greek one. And the earthquake took place here, and this is a signature before, 2 weeks before this earthquake. This is a very good signal. So it was working, but we had to stop. All right. So now I come to the big one. What happened on the 311? Yeah. What happened seemed to be like this. Tsunami, I don't know exactly how many meters, but it's something like 15 meters. Nuclear plant melted down. And it was a magnitude 9. Was this an unimaginable event? That was a lot discussed about after the earthquake. Okay. In fact, very few people had any anticipation for that. And just in order to illustrate this scale of business, magnitude and source of the earthquake. Magnitude 5 is this small, 6 about this one, this small. Magnitude 7, this one. Magnitude 8 becomes like this. And let's see, if it becomes magnitude 9, the area concerned would be like this, and displacement will be about this order. So these earthquakes are so different from small one to big one in size. Okay. And actually what happened is, this is Japan here, and this is the earthquake after March 11, in, I don't know, until May 14. But this big area is the earthquake origin. And many earthquakes, aftershocks, we call triggered earthquakes, occur far away from this, even from this area. This is something, a completely different animal we have ever had in Japan area. Okay. But this type of earthquake could have been anticipated because it has been taking place various places, starting from something like here, Chile, Alaska, and Kamchatka, and Aleutians, then Sumatra, Chile again, and Tohoku. Okay. So they are like this. This is time, 1900, 2010. So they seem to occur in cluster, not evenly distributed somehow. So they are taking place on different places around the world, I mean the Pacific, but they seem to be somewhat organized. We don't know why. Okay. Anyway, it could have been anticipated. But they did not anticipate, I mean seismology. And this is another evidence of tsunami, large tsunami many years ago, 869, there was a tsunami, and this red one shows the evidence of the sediments, of tsunami sediments. And this is the bay and the area, it's a place called Ishinomaki, where Chao Shin Lee and myself and your Vice President, Lu-san, was with us to look at this just a couple of weeks ago. And this is the geographical survey results of this year's tsunami-affected area. And comparing this is the same size as the map. In fact, they are the same thing. So, and just about 1,000 years ago, there was more or less the same type of earthquake took place. Okay. But what happened is, nobody expected, not expected in long term, of course. They thought it should never happen in Japan. No short-term precursors, seismologically, or GPS. And important thing is no press rip observed. Press rip is the only seismological model says big earthquake has to start with press rip. And this is their philosophical basis for prediction. But never been observed anywhere. And this time either. So, okay. So no seismic short-term precursors, no. But, non-seismic, no. That means non-seismic means electromagnetic. If there is this thing ever existed or not. Yes, but not so obvious ones so far. So not so dramatic, okay? Right? Only TEC data. TEC is total electron content, I guess, on the ionosphere data. It just was found 40 minutes before the big earthquake. And this could be something, but 40 minutes may be too short for anything, but still this is a new observation. But what I'd like to say, some very interesting discovery came from seismic data this time. But before going to that, I should just review the situation with the electromagnetic. This is they are using VLF, LF, broadcasting, or more or less, waves. And these red ones are receiving stations, and these blue diamonds are emitting stations. So between these receiver and the emitter, there is a sensitive area. So if anything happens, it should be this area or this area. So if they have cover like this, they can be pretty well good in identifying the possible location and magnitude. Okay, but in the case of Tohoku earthquake, it was out in the sea. So none of these internal system worked. The only possibility was the station from the United States. And here's the, this is the epicenter. And these are the station. And they saw something here. But in this case, they saw something, but all they can say is earthquake may come between this and United States. So it's not very easy for the school. But still, it's not hopeless. So, okay. But I'd like to finish my talk. Fluctuation on order parameter kappa 1, which is a variability of kappa 1, which is defined like this. This is what called deviation, and this is the mean value of kappa 1. Changed drastically near the main shock. I'm not going to talk about kappa 1. Yes, come on. Yeah. So, this is a conclusion, but let's go next. I just want to go straight. Go one more. This is the results. Tohoku earthquake, there's a kappa 1 variability. And comes up like this. And we found it rather amazing. And we checked this, if the same thing happened for Kobe. And Kobe case also, see. And in this axis, time is not exactly the conventional time. It's what we call natural time. So we convert this to conventional time. This curve becomes like that. This is the Earth time of the earthquake. Such an amazing precursor has never been observed for anything, for anybody. So we are rather excited about it. Okay. So maybe this could be a revolutionary discovery. So we are excited, but the study has just started. So if I want to explain what kappa 1 is, it takes another 1 hour or 2. So I will not go into that. But this morning, I got this result from a friend who are working on this. They are actually Greek people. We are sending Japanese earthquake data every day to them. They have a good soft working. And this is not exactly the same kappa 1, but in principle they are the same. And this value was changing like this, like this. And before the year earthquake, it was higher like this. So if it go down, earthquake will not come. But if it goes up like this, it can be very dangerous. And in fact, small earthquakes take place like this, and they seem to be connected somehow with the change of this, but nothing has been established on this. Next slide. Okay. So I thank you very much. This is the Professor Chaoshing Ni. 2 weeks ago or 3 weeks ago, we were in Tohoku. Thank you.
Thanks. I think we can have 1 or 2 quick questions. Yeah. Thanks, Liu.
Thanks for your excellent speech. It's very informative, but very sorry that the time is too limited. I just have one question. I'm not sure if I catch the point. It is about the prediction of the precursor. Is the earthquake predicted? I mean, the precursor predicted before the earthquake?
Sorry, I couldn't.
We observe.
His
I mean,
question is the earthquake predicted, the precaution is predicted? No. This is after.
Precursors, by definition, takes place before the earthquake. But if we can find it before the earthquake and can predict the earthquake by this precursor, your prediction is successful. But so far, practice of this type of prediction has been successful only in Greece. Only in Greece.
in Greece.
Yeah.
Okay. For the time being, so we have to move. But later, when come to my time, you can ask my teacher more questions. That's no problem. All right. Our next speaker will be Professor Tom Hildy. Again, is my teacher in Texas A&M.